Welcome to the Explainer. Today, we're tackling a topic that honestly trips up a lot of folks, polynomial division. I know, just hearing the phrase kind of conjures up these nightmare images of endless chalkboards covered in variables and exponents, right? It sounds totally intimidating. But stick with me, because as we break down the math, a really clear path starts to emerge. We're going to strip away all that confusion and look at exactly how these mathematical gears turn together.
So here's our roadmap for today. We'll start with the anatomy of a division, move right into polynomial long division, check out a massive time saver called the synthetic division shortcut, and finally, wrap things up with some theorems and the ultimate payoff.
Okay, section 1, anatomy of a division. Let's dive in.
Take a look at this. 105 divided by 5 equals 21, with a remainder of 0. You know, you've known how to do this for years. 105 is our dividend, 5 is our divisor, 21 is the quotient, and 0 is the remainder. Now, compare that to the polynomial equation on the right. P of x equals d of x times q of x plus r of x. Sure, it looks like a bunch of alphabet soup, but here's the secret. It's literally the exact same architecture. The polynomial dividend equals the divisor times the quotient plus the remainder. Same exact concept, just wearing a slightly more complicated algebraic outfit.
So the absolutely crucial takeaway here is that just like the number 5 is a perfect factor of 105 because, well, it leaves a remainder of 0, that exact same rule applies to polynomials. If your remainder, that r of x, is 0, boom, your divisor is a bona fide factor of your starting polynomial. Keep this in your back pocket, because this zero remainder rule is basically the foundational secret to everything we're going to look at next.
Moving right along to section 2, polynomial long division.
Now, if you've ever done long division with regular numbers, you honestly already know this rhythm. It goes like this. First, you arrange your polynomials in descending order, right from the highest exponent all the way down to the lowest. Then, you divide the leading term of your dividend by the leading term of your divisor. Take that result, multiply it by the entire divisor, and write it right underneath. Then, and pay attention because this is where everyone slips up, you subtract that entire polynomial. You got to make sure to distribute that minus sign carefully. Finally, bring down the next term and just repeat the whole loop. You keep running this cycle until the degree of your remainder is strictly less than the degree of your divisor. It's really just a procedural checklist.
Before we move on, though, I have to warn you about a massive trap that catches pretty much everyone at least once. If your dividend is missing a term, you absolutely must, and I mean must, use a 0 coefficient as a placeholder. For instance, if you're working with x cubed plus 5x minus 2, wait, you're missing an x squared term. You literally have to write it out as x cubed plus 0x squared plus 5x minus 2. If you skip that 0 placeholder, your columns simply won't line up, and it will completely derail your entire equation. Trust me, do not let a missing 0 ruin all your hard work. All right, let's look at section 3, the synthetic division shortcut. This is where things get really fun.
Okay, but there is a critical warning to heed right off the bat. When you're setting up synthetic division, you have to extract your c value by flipping the sign of your divisor. So if your divisor is x minus 4, your c is just a positive 4. But if your divisor is x plus 4, you actually have to use a negative 4. The absolute safest way to find c without messing up is to just set your divisor equal to 0 and solve for x. Easy peasy.
Once you have your c, the steps are brilliantly simple. You identify c, and then you write out only the coefficients of your dividend in descending order. And yes, remember to use that 0 for any missing terms. Notice what we're doing here, guys. We are completely bypassing all those messy variables. No more writing out x to the 5th power over and over again. You just set up your numbers, bring down the first coefficient, multiply it by c, and then, unlike long division where you're always subtracting, here you just add down the column. It's a total game changer. And this visual grid makes the whole process incredibly clean. Check this out. Your c goes on the far left. Your coefficients go right across the top row. You just drop that first coefficient straight down to the bottom row. And then you bounce. Multiply that bottom number by c, pop the result in the next column's middle row, and add straight down. Multiply, add. Multiply, add. It perfectly aligns the whole shebang into this fast, rhythmic process. So once you hit the end of the grid, you're left with this bottom row of numbers. But what do they actually mean? To translate this back into algebraic reality, look at the very last number on the far right. That right there is your remainder. Every single number before it represents the coefficients of your new quotient. And because we divided by a linear polynomial, the degree of your quotient is always exactly 1 less than the degree of your original dividend. So say you started with a degree 4 polynomial, your bottom row coefficients now belong to a degree 3 quotient. Actually, it's incredibly elegant when you see it all come together. Which brings us to our final part, section 4, theorems and the payoff. Let's take a quick pause here, though. Why does this process actually work? And what is it really telling us about the underlying functions? We're going to shift gears now from merely solving a procedural math problem to understanding some truly incredible mathematical connections. Enter the remainder theorem. This basically states that if you divide a polynomial, f of x, by x minus c, the remainder you get is exactly equal to f of c. I mean, really think about what this means. That final member sitting at the bottom right of your synthetic division grid, it's basically a magic trick. It gives you a highly convenient, super fast way to evaluate complex polynomial functions. Instead of plugging a number directly into some massive equation and calculating it out to the fifth or sixth power the hard way, you can just run a quick synthetic division. Boom, the remainder is your answer.
And that brings us right to the factor theorem. A polynomial has a factor of x minus c if and only if f of c equals 0. Let's connect this all the way back to the very first section of this explainer. If the remainder is 0, you haven't just solved a division problem. You have mathematically proven that x minus c is a perfect factor of that polynomial. It's all connected.
These concepts combine to form what I like to call the ultimate cheat sheet for functions. Think about it. If you use synthetic division with a c of 3 and your remainder comes up to 0, then f of 3 equals 0. Instantly, you know 3 totally different things. First, you know that 3 is a 0 of the function. Second, you know that the expression x minus 3 is a perfect factor. And third, visually speaking, you know that the coordinate 3, 0 is an exact x-intercept on the graph of that polynomial. If you know just one of these interconnected pieces of data, you instantly unlock the whole set.
So, look at how far we've come. We started with what looked like terrifying algebraic long division, and we've arrived at a literal master key for understanding functions. By using polynomial division, and especially leaning on that synthetic shortcut, you can easily evaluate functions, find perfect factors, and pinpoint exactly where a graph crosses the x-axis. As you move into even more advanced math, how might these exact division tools unlock the hidden zeros of crazy, higher-degree polynomial graphs? Well, that is the next great puzzle for you to solve. Thanks for hanging out with us for this explainer, and hey, happy calculating.